Here's an overview of fat metabolism. On the left we have fatty acid synthesis, and on the right we have fatty acid breakdown. Let's first start by talking about fatty acid synthesis. So fatty acid synthesis is pretty intuitive if you think about it. One of the big major things that we have to know about this process is that it is going to occur during high energy states. And this should make sense because if we're starving, then we don't want to use ATP to store fat for future energy use because we need that energy right now. So during high energy states, one of the big things that one of the big hormones that are active is insulin. Right, so for example, let's say that you had a giant meal, and when you had that giant meal, then insulin gets released in order for that glucose to enter your cells. So when insulin gets released, it is the major anabolic hormone in our body. It is going to upregulate protein synthesis. It is going to increase glycolysis because we need to produce energy for normal cellular processes. And so with insulin, we're going to increase glycolysis. And then we're also going to ultimately increase citric acid cycle and the electron transport chain to produce ATP. Now, when we have high levels of ATP, we might want to store that energy for future use in the form of fat. And the body is basically going to communicate this information saying that, hey, we have high levels of ATP, so instead of generating even more ATP by continuing with the citric acid cycle, let's stop at a step so then we can shunt this metabolic process to a fat formation for future energy use. And the step where this communication occurs is at the level of isocitrate dehydrogenase. So as you can see, high levels of ATP as well as NADH are going to inhibit isocitrate dehydrogenase, and when this occurs, we're not able to continue with the citric acid cycle. So when we're not able to continue with the citric acid cycle, then we won't be able to get those reducing agents, the electron transport chain for oxidative phosphorylation, to produce energy. So instead, this step gets inhibited, and in return we get high levels of citrate. Then citrate is going to transport it to the cytosol, where then it can continue the steps of fatty acid synthesis. Now, citrate is then going to be converted into acetyl-CoA and then malonyl-CoA. The conversion of acetyl-CoA to malonyl-CoA is done by the enzyme acetyl-CoA carboxylase over here. And this enzyme is upregulated by citrate as well as insulin. So as we said, we ate a big meal and we have high levels of insulin, and we also have high levels of citrate because we have a lot of ATP from the meal that we just ate, and so we want to inhibit this step so that we can, instead of generating even more energy, we can generate fat. We can produce fat for future energy use. So that is why we're also going to have high levels of citrate, and both of these things are going to upregulate acetyl-CoA carboxylase to convert acetyl-CoA to malonyl-CoA. So now we're going to have high levels of malonyl-CoA. And the significant thing about malonyl-CoA is that it is an inhibitor of carnitine acetyltransferase 1 over here. So on the right, we have fatty acid breakdown, right? And the significant thing about malonyl-CoA inhibiting carnitine acetyltransferase 1 is that we don't want both of these processes occurring at the same time, because that would be counterintuitive. We only want fatty acids, either fatty acid synthesis or fatty acid breakdown. So we don't want both of these processes to be occurring at the same time, because that will be counterintuitive. So malonyl-CoA, high levels of malonyl-CoA is the messenger that says, hey, we're actually trying to produce fatty acids, so let's not try to break down fats. And then malonyl-CoA is going to be converted to fatty acid, and then fatty acids are going to combine with glycerol to form ultimately triglycerides. And triglycerides are the major component of fats in the human body. Now let's take a look at fatty acid breakdown. So we're starting with triglycerides, which are the major component of fats in the human body. And triglycerides are broken down to glycerol and fatty acids by the enzyme hormone-sensitive lipase. And this enzyme is going to be upregulated by glucagon, catecholamines, as well as ACTH. And this should make sense because these are all hormones that get released during the times of fight or flight. So when our sympathetic nervous system is in charge, all these hormones get released, and we need energy to, let's say, like we're running from a bear, and then we can also provide that energy by breaking down fat. So it makes sense that all these hormones are going to upregulate hormone-sensitive lipase. It also makes sense that insulin inhibits hormone-sensitive lipase, because insulin is the major anabolic hormone in our body. So if we have high levels of insulin, we already have enough energy in our body. That's what that means. We're in a high energy state if we have high levels of insulin. So it doesn't make sense to break down triglycerides to form even more energy. And that is why in type 1 diabetics, when insulin levels are low, it is not going to be able to inhibit hormone-sensitive lipase. So then we're going to ultimately produce energy through the breakdown of fatty acids. And then if we're producing fatty acids, then if we take a look at the end, these fatty acids can then be converted to acetyl-CoA and then enter the citric acid cycle all over the body except for the brain to be used to generate energy. And remember, we can't use fatty acids in the brain to generate energy. The brain only uses glucose and ketones for energy. So when fatty acid synthesis is upregulated dramatically, the citric acid cycle gets overwhelmed, and that's when acetyl-CoA, instead of entering the citric acid cycle, it is going to be shunted to form ketones. Now, fatty acids are going to be converted into acetyl-CoA, and then acetyl-CoA through carnitine acetyltransferase 1 enzyme can be combined with carnitine to form acetylcarnitine. So fatty acids are negatively charged, and the mitochondrial matrix is also negatively charged. So as you can see, we have a problem because both are negatively charged, so they will repel each other. So we need a certain shuttle to get acetylcarnitine to the mitochondrial matrix, and that is done by the carnitine shuttle. Carnitine shuttle is what gets uh, acetylcarnitine to the mitochondrial matrix over here. So then acetylcarnitine can be formed into acetyl-CoA, and in the process it is also going to generate these reducing agents like FADH2 and NADH, and these can also be used in the electron transport chain to provide energy for us.